Welcome back, Marauders. This is video 6.1, the wave nature of light. In this section, we're going to start talking about light, and the reason for that is that we want to understand the atom and how the parts within the atom are arranged. Atoms are much too small for us to see inside and see how the protons, neutrons, and electrons are behaving directly, but we can make some conclusions about how the electrons are behaving and how they're arranged by looking at the light that is absorbed or given off by atoms. So we're going to first start to learn a little bit about light in this section, and then later in the chapter we'll see how that applies to, or how that helps us understand the way the electrons are arranged within the atom. So light is one type of electromagnetic radiation. Other types are radio waves, microwaves, infrared, and the visible light, ultraviolet, X-ray, and gamma rays. They're all electromagnetic radiation, and they differ by the size of the wave. So the really big waves with a large wavelength, the peaks are really far apart, would be things like radio waves, microwaves. And then the things with the really short wavelengths, X-rays and gamma rays, have a really short wavelength. Visible light is somewhere in between. Visible light is from about 400 nanometers with the violet up to 750 nanometers with red light. So we can see waves that are within the range of 400 nanometers to 750 nanometers. Anything bigger or smaller than that, it's the same type of electromagnetic radiation, but our eyes are not able to detect it. So there's two really important equations in this section. The first one is C is equal to lambda times nu. So in this equation, C stands for the speed of light. And the speed of light is a constant. It's 3 times 10 to the 8th meters per second. And it's the speed of light. It's not just for visible light, but any of these waves, so the radio waves, the microwaves, the X-rays, they all travel at that same speed, 3 times 10 to the 8th meters per second. Lambda stands for wavelength, so it's the Greek letter lambda, and it stands for wavelength. Wavelength is the distance between peaks on the wave. So if we have a wave that looks like this, then the wavelength is from here to here. That distance is the wavelength. And depending upon what the wavelength is, we're going to view it as a different color, or maybe it might be outside of our range of visible light. And then the nu, this is frequency. And frequency is how many waves come by per second. So how many waves come by per second? If you're looking at one place and you were just counting how many waves came by, that would be the frequency. How many waves come by per second? So wavelength and frequency are inversely proportional. If a wave is really large, then it's not going to come by as frequently. And if it's a really short wave, then it has a high frequency. The other equation that's pretty important is this one, which you can calculate the energy. And so energy is going to be measured in joules, just like in our last chapter where we were measuring other types of energy. So in this equation you have E for energy. H is a constant, and it's called Planck's constant. And Planck's constant has a value of 6.626 times 10 to the negative 34 joules times seconds. So that's a constant, it's always going to be the same. And then just like in this equation, the nu is standing for frequency. And that's how many waves come by per each second. So we can try to use these two equations in a problem like this. How much energy is in one photon of light with a wavelength of 656 nanometers? 656 nanometers. We want to figure out how much energy is in one photon. A photon is like the smallest piece of light that you can have. So we're going to use the two equations that we just learned. So C, the speed of light, is equal to the wavelength times the frequency. And we can use the equation for energy is equal to Planck's constant times the frequency. So we'll start by looking at the wavelength, and we'll put it into this equation. So C, the speed of light, is 3 times 10 to the 8th meters per second. And we can see that our wavelength is in nanometers. So we're going to convert the nanometers to meters. So we'll have 656 nanometers, and we'll convert that into meters from nanometers. So 1 meter is equal to 10 to the 9th nanometers. So when we do this, we get 6.56 times 10 to the negative 7 meters. And so now that that's been converted, we can put the wavelength in. So this symbol right here, lambda, stands for the wavelength. So 6.56 times 10 to the negative 7 meters. And then times frequency. So divide both sides by 6.56 times 10 to the minus 7. And when you do that, you get, let's see, frequency is equal to 4.57 times 10 to the 14th. Okay, the units right here, meters will cancel out with meters, and it'll be 1 over seconds. There's a couple different ways you can write it. You'll see it written out like this, 1 over seconds. It could also be written out as seconds to the minus 1. And then it could also be written out as Hz. So hertz means waves per second. So it's another way you may see it. Hz means the same thing as per second. So now that we have the frequency, we can use the second equation to find the energy. So energy is equal to Planck's constant. So Planck's constant is going to be given to you. It has a value of 6.626 times 10 to the negative 34 joules times seconds. And then the frequency, which we just found, 4.57 times 10 to the 14th, 1 over seconds. So you can see how seconds will cancel out, and then when we get joules, and we multiply these two numbers together, you get 3.03 times 10 to the negative 19 joules. And the seconds canceled out. So there's an extremely small amount of energy in each photon of light. A photon is extremely small. We never just notice one single photon of light. We always see millions and billions of photons together.